In Hamilton path, every vertex, every graph path visit exactly once. It is a Hamilton path which starts and stops at the same vertex. Very important formula for finding whether it is Hamiltonian path or not. So starting point is A and the ending vertex also A. So it is a closed walk. Hello my dear students, welcome back to my new session. I am Shweta, Computer Science faculty. In my previous session, I have discussed about representation of graph. Graph can be represented in many ways, but the most important representation of graph is adjacency matrix and adjacency list. So I have explained adjacency matrix and example problems and adjacency list. So today I am explaining the new concept called Hamilton graph and planar graph. So what is this Hamilton path, Hamilton graph and Hamilton circuit? So Hamilton path is also known as Hamiltonian path, also called a Hamilton path. Hamilton or Hamiltonian path is a graph path between two vertices of a graph that visits each vertex exactly one. Listen carefully. In Hamilton path, every vertex, every graph path visit exactly once. And if a Hamiltonian path exists whose end points are adjacent, then the resulting graph cycle is called a Hamiltonian cycle or Hamiltonian cycle or Hamilton cycle. So, Hamilton path visits each vertex exactly once. Example, here A to B, C and D. So from A to B and from B to C and from C to D and from D to A. So here what is the circuit of this graph? A to B, B to C and C to D. Again D to E. A to B, B to C, C to D and again D to A. So, observe this circuit. So, here path visit A to B, B to C, C to D. So, it visits each and every vertex exactly once and again it will reach to the same starting point, that is A. So, if the starting and ending vertex should be same, called as closed path. In my previous session, I have discussed this open walk and closed walk, right? So, in closed walk, starting point, vertex point and ending vertex point should be same. Then it is considered as it is a closed walk. So, Hamilton path is a closed walk and it visits each and every vertex exactly once. Clear? This is an example for Hamilton path. And also you can give this example A to B, B to C, C to A. A, B and C. So, A to B, B to C and C to A. Again, circuit is A to B, B to C, again C to A. So, starting point and ending point vertex should be same. So, it is a closed walk. Clear? This is an example for Hamilton path. And in Hamilton path, it visits vertex exactly once is called as Hamilton path. Hamilton path means visits exactly once. And Hamilton circuit means starting point, starting vertex and ending vertex are same. This is called as Hamilton circuit and Hamilton path. Don't get confused. This is Hamilton path and this is Hamilton circuit. So this is an example for Hamilton circuit. A to B, B to C, again C to A. Starting and ending point should be same. This is considered as Hamilton circuit. And Hamilton path means visit each and every vertex exactly once are called as Hamilton path. So one more example I'll write A to B, B to C, C to D. So this is A, B, C, D, E. So A to B, B to C, C to D, D to E. So here each vertex visits exactly once. This is an example for Hamilton path. Clear? And this is an example for Hamilton circuit. A, B, C, D. So starting point and ending point should be same. So next is Hamilton circuit. So already I have discussed this on Hamilton circuit. It is a Hamilton path which starts and stops at the same vertex. It should be connected graph. It should be closed walk. So already I have explained. It should be connected graph and is a closed walk. So starting and ending vertex are same. And another example, A to B, B to C, C to D, D to E, E to F, F to E. So starting point is A, again A to B, C, D, E, F and again A. So this is an example for Hamilton circuit. So you have many examples, you can give any other example also. But you have to write the circuit A to B, C, C to D, D to E, E to F and F to A. So starting point and ending point vertex should be same in Hamilton circuit. Next one, length of Hamilton path. So how to find out the length of Hamilton path? Let G be a graph of n vertices. Then G has a Hamiltonian path if for only two vertices U and V of G. I'll repeat. So example, here I have one graph A, B, C, D, F. So this is one graph. So in this graph, I will take only two vertices, whether it can be A, B or D, C or E, F, any other vertex you can take. But we have to use this formula for finding the length of Hamiltonian path. We have to find whether it is a Hamiltonian path or not. I'll use this formula, degree of U plus degree of V should be greater than or equal to N. Very important formula for finding whether it is Hamiltonian path or not, or finding the length of Hamiltonian path. Here I will take two vertices. You can take any other vertices. I will take B and C. So degree of B plus degree of C. So first you have to understood A, B, C, D, E, F. How many vertices are there? 1, 2, 3, 4, 5, 6. So N is equal to 6, right? So N is equal to 6 here. So now you have to find the degree of each vertex. So in my previous session already I have discussed this degree of vertex. So what is the degree of this B? 1 and 2. So degree is 2. What is the degree of this C? It is 2. Degree of D also 2, 2, 2 and 2, right? So each and every vertex degree is 2. So now I will add 2 vertex degree. Degree of B is 2. Degree of B is 2. Degree of C is also 2. Number of vertices is 6. So 4 is greater than or equal to 6. Is it true? It's false because 4 is not greater than 6. So the statement is false. So now it's not satisfied. It is not satisfies the Hamiltonian path because the condition is false. So Hamiltonian path does not exist. So this condition is not satisfied Hamiltonian path. So now again I'll take one more example. to find the length of the Hamiltonian path. It is A, B and C. So n is equal to 3. We have 3 vertices A, B, C. So n is equal to 3. So degree of A plus degree of B should be greater than or equal to n. This is a formula. So what is the degree of A? 2. Degree of B? 2. Degree of C? It is 2. So 2 plus 2. I'll take A and B. 2 plus 2 greater than or equal to 3. So 4 is greater than or equal to 3. Is it true? Yes, it is true. It exists. Hamiltonian path. It is very simple concept. So you can expect this question for 4 marks. Find the length of Hamiltonian path and they'll give the graph. So you have to find the degree of each and every graph and you have to prove that whether it is satisfying Hamiltonian path or not. Clear? This is an example for length of Hamiltonian path. And another example for length of Hamiltonian path. So first I will draw a graph. So here A, B, C, D and E. So first you have to observe whether it is a Hamiltonian path or not. So it should satisfy the Hamiltonian condition. So it should be a closed walk. That means the starting and ending point should be same and it visits each and every node exactly once. So now first we'll check the circuit A to B, B to C, C to D, D to E and again E to A. So again it reaches the same point. So A to B. What is the circuit? A to B, B to C, D, E and again A. We have 1, 2, 3, 4, 5. So number of vertices is 5. So starting point is A and the ending vertex also A. So it is a closed walk and it's satisfying the Hamiltonian condition. So now we have to check the length of a Hamiltonian path. So here degree of A plus degree of A and degree of E I'll take should be greater than or equal to 5. So what is the degree of this A? 1, 2, 3. Plus, so what is the degree of this E? 1, 2, 3, 4. So 3 plus 4, 7 is greater than or equal to 5. The condition is true. So it exists Hamiltonian path. So it is a Hamiltonian path. Clear? This example you can give for length of Hamiltonian paths. So by using this formula easily you can find out the degree of each and every vertex. But it should visit each and every vertex exactly once. Listen, one more thing I have to explain here. A to B, B to C, C to D, D to E and again E to A. It reaches the same point, right? Here, every vertex should cover but not the edges. Clear? Every vertex has to cover and it has to visit each and every vertex exactly once but not this edges. These two are the edges. No need to consider this. It has to visit each and every vertex exactly once. Clear? It has to cover the vertex only. So this is an example and the next example. So next one, A to B, B to C, C to D, D to B. So here A, B, C, D. So first you have to check whether it is satisfying the Hamiltonian condition. Hamiltonian condition means it has to visit each and every node exactly once. So A to B, B to C, C to D, D to B. It's not satisfying because A to B, B to C, again C to D, again it reaches to B, B to D to B. It's not satisfying because B is repeated twice. So this graph has not satisfied Hamiltonian condition. It does not exist Hamiltonian path. Another example. So A, B and C. We have three vertices. Check whether it is satisfying Hamiltonian condition or not. So A to B, B to C, C to A. But here we have D and E. So again C to D and C to E. So C is visited twice. A to B, B to C, C to A is okay. But here we have D and E. So C to D and again C to E. Here C is visited thrice because A to B, B to C, C to A and again C to D and again C to E. So it is not satisfying the Hamiltonian condition. Clear? And the next example. So A, B, C, D and E. So A to B, B to C, C to D, D to E, E to F. So E to A. So again it reaches the same point. It's satisfying Hamiltonian condition. So now we'll check whether it is satisfying the length of Hamiltonian condition or not. So degree of A plus B greater than or equal to n. What is the value of n? 1, 2, 3, 4, 5. What is the degree of A? 1 and 2. Plus degree of B is 1 and 2. 4 is greater than or equal to 5. Is this true? No, it is not true. Not exist Hamiltonian path. Clear? And the next example. A, B, C, D and E. So now check whether it is satisfying Hamiltonian condition or not. A to B, B to C, C to D, D to E and E to A. It's satisfying because starting point is A and B, B to C, C to D, D to E and E to A. Again it reaches the same starting point. Listen, here we have one edges. If you are not visiting the edges also okay, but it has to visit each and every vertex exactly once. So it is A to B, A to B, B to C, C to D, D to E and again E to A. So it's satisfying the Hamiltonian path condition. So now we'll check the degree of vertex B and plus degree of C greater than or equal to n. So what is the value of n? A, B, C, D, E. So n equals 5. So degree of B is 1, 2, 3 plus and degree of C is 1 and 2. So 5 is greater than or equal to 5. So it's satisfying the condition. So 5 is greater than, it's not greater than, but it is equal to 5. Clear? So these are the examples for length of Hamiltonian graph. So easily you can find the length of Hamiltonian graph by using this formula. Degree of U plus degree of V is greater than or equal to n but not less than or equal to n. Don't get confused. It should be greater than or equal to n. So first you have to find whether it is a closed walk or not. And you can find the degree of each vertex. And in Hamiltonian path, it has to visit each and every node exactly once. Each and every vertex exactly once. Then we can consider it is a Hamiltonian path. And the next one is planar graph. 2 marks question. A graph G is said to be a planar if it can be drawn on a plane or a sphere to that no two edges cross each other. This is very important sentence. No two edges cross each other at a non-vertex point. Here you have one example graph. A to B, B to E, E to D, D to C, C to A. Again, we have reached the same point, but here no two edges cross each other. So two edges are crossing each other. So it is not a planar graph. So two edges are crossing each other in this point. So it is not a planar graph. Clear? So now you can see the another diagram. So A to B, B to E, E to D, D to C and E to A. So this is an example for planar graph. No two edges cross each other. Then it is a planar graph. Another example for planar graph. So here two edges are crossing each other. It is not a planar graph. Clear? So no two edges are crossing each other are called as a planar graph. 2 marks question, so you can give this example. So another example. Is this planar? You just think about this graph. Is this planar or not? And the next example. And again, is this planar graph or not? What is the answer? Is this planar graph? Yes, it is a planar graph. Because no two edges are crossing each other, but it is intersected at the ending point. Clear? So is this planar graph? No, it is not a planar graph because two edges are crossing each other. Clear? It is not an example for planar graph. And the next example. Is this planar graph? Is this planar graph? It is not a planar graph because two edges are crossing each other. So it is not a planar graph. Clear? And the last example for planar graph. Is this planar graph? Is it true or not? Yes, it is a planar graph because no two edges are crossing each other. So these are the example for planar graph and non-planar graph. It is not a planar graph, it is a non-planar graph. It is also a non-planar graph and it is a planar graph and it is not a planar graph and it is a planar graph and it is non-planar graph. So this is about your planar graphs and examples. So today you learned the very important concept called Hamiltonian path, circuit and length of Hamiltonian path. It is very important question. And also you learned the concept called planar graph. In my next session, I will come with a new concept and very important concept called shortest path problems. Definitely there will be a problem on shortest path problems. So it is 8 marks question. It is compulsory question. So in my next session, I will discuss about shortest path problems. Thank you.